deep latent variable models part is also going to overlap a little bit with what you learned last evening, but we're going to use some of the tools that you learned in the variational inference part of this course. Let's jump to the introduction to generative modeling. So the setup in generative modeling is that we observe some data. We could call it x1 to xn. It could, for instance, be this celeb8 data set. And our goal in generative model is to learn an approximation of this data generating distribution, so sort of the underlying distribution that was used to generate this data set that's of course not accessible. And an outcome is that we'll be able to generate new plausible images from this learned model. So why probabilistic generative modeling? And sort of what is sort of the idea? So to take a quote from the David Mackay book, then a forward generative model describes the process assuming to give rise to the data. That's how we can think about generative modeling. So in generative modeling or unsupervised modeling, then we model the joint density of all the variables we have accessible. And typically we assume some factorization, and if you do like old school generative modeling, has anybody seen a graph like this before? Yes, so it's sort of a typical graph is sort of, we got some variables, we got whether or not it's cloudy, whether or not the sprinklers are on, whether or not it's raining, and then we got whether or not the grass is wet. So the idea is that these are all random variables, and whether or not it's cloudy, its binary variable determines whether or not the sprinklers are on, or whether or not it's raining. If it's cloudy, then most likely it's raining, and if it's cloudy, most likely the sprinklers are not on. And there's two explanations for why our grass could be wet. Either the sprinklers are running, or it could be raining. So sort of old school generative modeling, we would write down these graphs. Once we then learn the joint distribution over all these variables, then we can answer probabilistic queries. So the idea in generative modeling is that learning this joint is the hard part. Once we learn this joint distribution over all our variables, then the easy part is to answer all the queries about sort of our using our model. So one thing we can, for instance, do is once we learn this joint distribution over these 4 variables, we can sample from them. We can ask about what's the probability or the density of the variables. We can do marginalization. So we, for instance, up here we just ask, marginalize out cloudy, sprinkler, rain, and we just ask what's the probability of having wet grass. We can do conditioning. So like conditioning here, we can ask what's the probability of one variable using the other. That could be classification. So we say, given that we know it's cloudy, whether or not the sprinklers are on, whether it's raining, then we can ask what's the probability of having wet grass. We could also sort of use this for doing missing data imputation. We could do something like, we could fill out missing values for sprinkler if we know the rest of the variables. We can calculate expectations. That could be for doing moments, like the mean of the distribution, and we can also do maximization. The idea is that we learn the joint distribution, and then once we learn the joint distribution, then we can answer all these queries. What about the probabilistic part? Well, so there's this different 2 reasons why we want to sort of have probabilistic generative models. One is that we want to be able to generate afterwards, and if we want to generate, then we need to have some sort of randomness in there. That's one reason for it being probabilistic, and the other reason is that the probabilities just gives us a consistent framework for doing reasoning under uncertainty. So we can do, once we learn the joint distribution, we can do all this type of reasoning. It's sort of a consistent framework for doing that. But the main thing here is that we're able to do sampling. And why on earth would we want to do sampling? And particularly, why would we want to generate new plausible images? One explanation is, of course, just that it's cool, right? If you look at, these are all generated images, and that's pretty cool, right? You can generate some cool images. But it's also because it can have like a unexpectedly big impact on society, as we already seen. If you look at large language models, they have had a significant impact on the society, and the same with these deep generative models for like DALL-E or Midjourney or Stable Diffusion. You also see how they sort of have big societal impact in many places. And it's also not just limited to pretty images and text. We can also sort of, there's these models for generating audio. There's models for generating molecules. I'm sure Victor will mention this this afternoon. And there's also, this is sort of a modeling task where it's used to do character control. So we could also use probabilistic models for doing control. Okay, so what is it we want to do with these models? So we assume I've sort of specified a model family that's parameterized by some parameter theta. Then we want to find a good setting of our parameters such that our model is still very abstract, is very close, our model distribution is very close to the data generating distribution. So what is it we want to do? We can sort of think about, we have our model family here. This is all the different models we can specify with our set of parameters. And then we want to find the model that's closest to a data generating distribution. So we want to minimize the distance in some abstract sense between the data generating distribution and our model family. And you already learned about ways we can calculate distances between distributions. We already, in the first couple of days, saw the Kullback-Leibler divergence, which is basically just measuring the average difference between, in log densities between P and Q. It's not a full distance, but it has these distance-like properties that is bigger or equal to 0, and it's 0 if and only if the two distributions are the same. So what we can do is that we can say, oh, we want to find a good theta for our model such that they are equal to each other, and then we can pick the KL to minimize. So we want to find theta such we minimize the KL divergence between our data generated distribution and our model. And then we just write out this KL. So we can write the KL as the difference between two expectations. The expectation of the data generated distribution with respect to the data generated distribution, and the expectation of the log probability of our model with respect to the data generating distribution. And if you look here, then we want to minimize the KL with respect to this parameter of the model parameter, and we see this first term here doesn't depend on the model parameter. So we just remove this term here, and if we want to minimize the KL, then we just need to minimize this term here. Of course, we don't have access to the data generating distribution. We just have access to samples from the distribution. So I cannot calculate this one, but I can calculate a Monte Carlo estimate of it. So I can just take my samples, and then I can take the mean of the log probability of our samples, and then that's approximation of this expectation. So if we want to minimize the KL between our data generating distribution and our model, then we want to find the parameters that or either minimizes the KL, or if we remove this minus here, it maximizes the mean log probability of mean log probability of our data according to our model. And if you see this, this is exactly the log likelihood function. You should remember this is the log likelihood function. So it means that we can think about, this is sort of just an explanation for why we might want to maximize the log likelihood. Because we can think about if we maximize the log likelihood, then we minimize the distance, the KL divergence between our data generating distribution and our model. So in general, for these lectures, what I'll assume is that we want to do maximum likelihood estimation, which is different from what you've sort of been taught so far, because you've mainly been taught, as far as I understand, a Bayesian perspective, that we want a posterior over our parameters. But in this part of in my presentation, we'll assume that we want a maximum likelihood estimate. So we're given some model family, and we're given some observations, and then our objective is to learn the parameters by optimizing the log likelihood function, and then we find what's called a maximum likelihood estimate. Okay, so if we look at modern deep generative models, this is sort of the main classes. We got deep latent variable models, or VREs. We got the autoregressive models. We got normalizing flows. We got energy-based models. We got generative adversarial networks, and we got diffusion models. Today, I'm going to focus on the deep latent variable models, the normalizing flows, and then this afternoon, you'll hear more about diffusion models. So the first part I'm going to talk about are deep latent variable models. So what is the idea behind a latent variable model? You've already seen latent variable models, but let me sort of reiterate and sort of give at least my perspective on latent variable models. So generative process in a latent variable model, we can draw the graphical model like this. We observe the X, we don't observe the Z, and the generative model, generative process that we sample this latent variable from P of Z. Once we sample Z, then given Z, we can sample X. And one of the main ideas behind latent variable models are the manifold hypothesis. The hypothesis is that Z has a lower dimension than X. So we can, for instance, imagine that we have these pictures of horses over here. The generative process is that from some lower dimensional space or manifold, we draw samples, and then we use that to generate these high-dimensional images. So the hypothesis is that data isn't really living in this full D-dimensional space. It's actually living in a lower dimensional space than the space we observe data in. And the assumption is typically also that we got some latent factors that we can describe on this manifold. So hopefully there'll be some direction in there that corresponds to, it could be in this case, the color of the horse. There could be some factor here in this latent space that describes the angle that the picture was taken in. There could also be some factor in that describes what does the background look like. Have we got sort of sky in the background? Have we got a green background? One more thing to note is that we don't observe this set. So sort of when we only observe X, and the way we can, using this model, we can describe the density of X is we have to marginalize out the set. So P of X is given by the joint density, so P of X given set multiplied by P of Z, where we marginalize out the set. All right, so the idea in deep latent variable models is also that you already seen many of examples so far, you already seen examples of classical probabilistic generative models. We already tried to do Bayesian inference in various models the last couple of days. If we look at these old school probabilistic generative models, then they have this very well-founded framework for doing modeling, building, and inference and predictions. So we got this way of thinking about variables, how they depend on each other, and express them either as graphical models or we could program them up in Pyro. One issue is that if we want to do, if we sort of usually when we deal with old school probabilistic generative models, then they're sort of limited in complexity, because often we want conjugated priors to be able to express the posterior, and usually learning is also very expensive in these models. If we look at deep neural networks, then these are rich nonlinear models. They are scalable to very large data sets using stochastic gradient descent. Issues are that they only give point estimates, and they are typically discriminative and not probabilistic. So usually we use deep neural networks to do discriminative modeling, so do predictions. And at least one way I think about deep generative models is that they sort of combine the approximation abilities of the deep neural networks with the statistical foundations of probabilistic generative models. Okay, so let's dive into deep latent variable models. We already went through the generative process, but let's just put some more terminology on it. So we have set, that's the latent variable. In deep latent variable models, we usually assume that set is a continuous latent variable model, and we call P of Z the prior. It's not a Bayesian prior, but we still use the term prior for it. Then we got X, which is the observed variable, and we have P of X given set, which we call the observation model. Then in here, the way we sort of describe this observation model is that we have capital theta here. That's some parametric family which we call the output density. And we'll talk a little about sort of how we choose the output density in the next slide. And then we have F in here, which we call the decoder. So F here is a neural network or a deep neural network. And I thought I had, yes, and the role of this decoder is really to say, I sample my set, then I put the set into the decoder, and the decoder gives me the parameters of this output density. So one thing you can think, one way of thinking sort of a bit abstractly about a deep latent variable model is you can think a bit about it as a mixture model, except that we have a continuous latent variable instead of a discrete latent variable. Sort of the graphical model is the same as you have for a mixture model. And I'm sure, I think I saw on the slide that was also mentioned yesterday, you can also think it as a deep latent variable model as a nonlinear probabilistic PCA. So it's nonlinear because we got this nonlinear decoder in here. So let's talk a little more about sort of this output density. So the output density, that's a model assumption. But it sort of has to fit with sort of the type of data that we are modeling. So for instance, if we got discrete data, that could for instance be that if we have an image where each pixel can take, it's a grayscale image where each pixel can take values between 0 and 255, then we would typically have a categorical output distribution to say that the probability of x given z is a categorical over the x's, where we set the parameters of the categorical by the output of our decoder. So be something like this, that we take our set, put it into our decoder, and then we get the probabilities out for the different, in this case, 3 different classes in the categorical distribution. So if you have in the categorical setting, then we would have a softmax at the output of our network, because we have to ensure that the output of the decoder lies in the parameter space of a categorical, and for the categorical, the parameters need to lie in this probability simplex. If we had continuous data, we could, for instance, choose a Gaussian output distribution, and typically for a Gaussian, we would assume a diagonal covariance matrix. So assume we had that our data was 2-dimensional. We could have a decoder that looks like this, where we input a 2-dimensional set, and then we output the mean of the first dimension, the mean of the second dimension, and then the sigma, or the standard deviation for the first and the second dimension. And then we would need to make sure that these are non-negative, and one way to do that is we would typically say that the covariance matrix of our multivariate normal is sort of a diagonal one, where we take the exponential of these ones to ensure that they are non-negative. Okay, so let me just illustrate sort of the generative process in a deep latent variable model. So assume that our training data was binary MNIST that looks like this. And then the generative model is, we assume a 2-dimensional latent space. So you see that the latent space is lower dimensional than the output space here, because the output space is a binary variable to the power of 28 times 28. And the generative process would be that we sample our set for our normal distribution, then we run the set through this very simple decoder network. So it's a linear layer with a 10H activation function, and then another linear layer, and then we got a sigmoid activation function, because we want to make sure that we get values out that are valid parameters for Bernoulli, and valid parameters for Bernoulli are values between 0 and 1. So the way the generative process, if I sort of train this network, by the way, I think this is the network that they used in the original VIE article for the example. So even though it's a very simple network, it actually works. So the way the generative process works is we could sample a set. In this case, I sample a set over here at minus 1.2 comma a half. Then I run it through the decoder, and this is what I get out of the decoder. So this is a probability map. So it says over here the probability of being white is 0, and in here we've pretty much got probability equal to 1 for being white, and in here is probably 50-50 between black and white. So this is the output of the decoder network. And that's what we pop into this Bernoulli distribution, which means that we have to sample independently each pixel from this image. And if I do that, then I get something that looks like this. That it doesn't look as nice, but this is the output of the model. And I could do the same. I could sample another point up here, run it through my decoder, get this probability network, and then I could sample another image over here. So this is the generative process of a deep latent variable model. So you already heard about VAEs before, and some of you probably also heard about them outside this course. And one thing you probably notice is I haven't set the word variational autoencoder yet. And in fact, I haven't even mentioned an encoder. I'm pretty sure you know that there's an encoder in there somewhere, but I haven't mentioned it. And I think you should just spend 3 minutes discussing with your neighbor, you know, how has this sort of presentation been different from the one you saw yesterday and sort of other presentations you've seen of VAEs? Why haven't I mentioned this encoder? And what insights does it give not mentioning the encoder yet? So spend 3 minutes discussing with neighbor, and then we'll go through these questions. All right, I'm going to interrupt you now. It's very good to hear that you're all discussing, but let's talk about these questions. So anybody has a suggestion for answering the first question? So how has the presentation been different so far? Any answers? Yes, exactly. I haven't mentioned inference. That was but could you? There's also another way of saying I haven't mentioned inference. There's also what have I been focusing on so far? Yes, I haven't been mentioned learning, but sort of I've been focusing on the model description so far. Or sort of it's another way of saying exactly what you're saying. I haven't mentioned learning, so I've just been focusing on the generative model description, and specifically I very much focus on how we generate data with this model. So why haven't I mentioned an encoder? It's very related to what you just said. Anybody else want to sort of chip in here?
The encoder is not needed for generation.
Exactly, the encoder is not needed for generation. It's only needed for learning the model. And in fact, you could learn these models without an encoder. There's works on how you can learn these without an encoder. So it's actually not needed there, and it's not part of the model. And what sort of insights does it give not mentioning the model, or sort of the encoder yet?
I think it's good to separate the model from the...
Exactly. That's exactly the answer was looking for. It decouples the model from the inference assumptions, and that's also what this whole Bayesian approach to learning things like these models are not Bayesian, but it's very much what we do as Bayesians. Is that when we're Bayesians, we write up the best model that describes our data generating process, and then afterwards we bother with how to actually learn it. And it's very useful to think about what are the assumptions I put into the model, and what are the sort of additional assumptions I impose on the model when I learn it. Good. So the way we learn them, I already mentioned this, is we want to do maximum likelihood for these models, or for deep latent variable models. And it's what I've written down the likelihood function here, where we sum the log probability over our observation, and then we want to optimize this function with respect to the parameters. In this case, we have this latent variable in the model, which means that if I want to calculate log p of x, I need to integrate over z. And then when I'm optimizing, then this theta here, that's actually the parameters of our decoder. So we want to find sort of the settings of our decoder that optimizes the log probability of our data. The issue here is, of course, this integral over here. So I cannot directly, these should have been swapped, these 2 points. I cannot directly optimize this P of z, because this, once I have a nonlinear decoder in there, then I cannot calculate this integral in a closed form. If you have a latent variable model, then hopefully the first thing if you cannot calculate the integral in closed form, the first thing that should come to your mind is, oh, we can do expectation maximization. So do use the EM algorithm. But in this case, we cannot use the EM algorithm because for the same reason as P of X being intractable, then P of Z given the so the probability of the latent variable given the data, that's also intractable. One thing you could then say, oh, you learned about Monte Carlo estimates. And of course, we could do a Monte Carlo estimate of this thing. We could just say, oh, why don't I just sample my latent variable from the prior, and then I use that to do a Monte Carlo estimate of the log probability. But it turns out this has got super high variance due to the curse of dimensionality. So basically, the number of samples needed to get a good Monte Carlo estimate of this grows exponentially with the latent dimension.
Yeah, I don't understand that later point. Does your variance increase with dimension? I don't think that's the case.
In this case, yeah. So it's if you the variance of this estimator here, right? So the estimate, this Monte Carlo estimate here. If I increase the dimension of my latent space, then the variance of this estimator increases exponentially with the dimension of my latent space. Okay, yes, we can take that offline afterwards. But that's the case here. If you like, you just need more samples if you did to get a good estimate. If you just increase the dimension of the latent space. So what we use is, and you already learned about this, so I don't need to go through this in details because you already learned about variational inference, and last afternoon you also talked about amortized variational inference. So the way we learn this model is that we write down an elbow for the model, and the elbow of this model is that we introduce a variational distribution that we set over our latent variable called Q theta, and then we end up with this usual elbow that can be decomposed into a reconstruction term and what's called the regularization term. And this is a lower bound on the log probability or the log likelihood function. And it's amortized, and that means that our variational distribution here is actually a parameterized distribution that's conditioned on the x, and we're free to choose sort of any variational family, so any family of distributions, but we usually use Gaussians for a Gaussian for a variational distribution. And then we have a neural network in there again. We have the G network here, which is called the encoder or the inference network. And the role of this inference network is that we take a data point, we put it into the encoder, and then it transforms the data point into parameters of our variational distribution. And if we do this, then usually, if we imagine that we have a Gaussian prior and we also have a Gaussian variation family, then this KL has closed form, and then we don't sort of so this is easy to calculate, but this is the hard term to calculate. But if we don't have Gaussians, then you can use this form for the elbow instead, because you can always, we assume that we can evaluate our prior, but we cannot necessarily calculate the closed form KL divergence. Then if we use variation inference, you've seen this before, then this variation distribution, we can think about that as a tractable approximation of our posterior. So we can think about that the variation distribution that we learn Q of Z given X, that's approximation of the true posterior, so the probability of the latent given our X. And we can also get low variance gradient. We can also get low variance gradient estimates of the gradient of these expectations here using the repermutation trick that you also talked about yesterday. I just want to mention a little bit about I don't want to go into details with these things because you've already been through the details here, but I just want to mention two things about the repermutation trick. That one is that it's also known as it's known under many names. It's also known as the pathwise gradient estimator. And one way I like to think about the repermutation trick is that you take this expectation here, which is you have the expectation down here, and then you transform it into a stochastic part that's parameter free, and then a deterministic part that's parametric. So we sort of say the way we sort of you can think about the reparametrization trick is that the stochastic part doesn't have any parameters anymore, and all the parameters are transformed into the deterministic part of the expression. And then I want to mention that many distributions can be reparameterized. The Gaussian can be reparameterized, the beta, the gamma, the student T, and the Dirichlet distribution. Usually we use the Gaussian as our variational distribution, but we could also use a student T variational distribution. In the exercises, we're going to look at PyTorch, and in PyTorch distribution, then the reparameterization trick is implemented using this R-sample function. So if you take a distribution from PyTorch distributions and you call R-sample instead of sample when you want to generate samples from your distribution, then you know that if it has R-sample implemented, then that distribution is reparameterizable, and you can backprop through the sampling process of that distribution. It doesn't work for discrete variables, because with discrete variables, you can only, like, if you want to reparameterize them, you can only do permutations, but that's solved by you can use a relaxed discrete distribution, such as the Gumbel softmax trick. I just want to mention that if you sort of come across that you want to reparameterize discrete distributions. And I also want to mention that there also exist other Monte Carlo gradient estimators. The most famous one is for instance, the reinforced method. There's this review by Shakir Mohammed and others from 2020 where they go through all the different Monte Carlo gradient estimators. Okay, so I talked about deep latent variable models so far. The VAE, I like to think about the VAE as a special case of a deep latent variable model, because the VAE, the way I view it is, it's a deep latent variable model combined with amortized variation inference. If we combine those two, then we get a variational autoencoder. And the components of variational autoencoder is that we got the prior, sometimes in the literature it's also called the marginal distribution over set. Then we have this, what I call the observation model. You also see people calling this the likelihood or the stochastic decoder. Then we have the decoder itself. People pretty much agree on calling this the decoder. Then we have the variational distribution or the variational posterior or the stochastic encoder Q of z given x that we use in our elbow bound. We have the encoder inside this, the variational distribution. And then we have this elbow objective that we use to learn the VAE with. And then optimization is done by maximizing the elbow with respect to the parameters of both the encoder and the decoder using stochastic gradient descent, where we use the reparameterization trick to calculate the gradients, or the Monte Carlo gradients. So why is it then called a variational autoencoder? Well, let's revisit this elbow. If we look at this elbow, this is just repeating the elbow, and then assume we got Gaussian input, and let's also assume that we fix the mean or sort of the covariance matrix to be the identity for our normal distribution. So I have then my elbow looks like this. If we then look at the loss of an autoencoder, a classical autoencoder, then the loss of an autoencoder is the difference between our data point, and then if we take our data point, we encode it and decode it, and then we look at the squared we look at the squared norm between those two data points. If I look at this normal distribution here, then if I got a log normal distribution, then I can write a log normal distribution with the identity matrix as I remove the exponential, then I get minus a half, and then because I got the identity matrix as the covariance matrix, then I just get the squared norm, the squared norm, where I take the difference between my x, the mean, or sort of not the mean, but the squared difference between where I evaluate my normal distribution and the mean of the normal distribution. And then I have a normalization constant over here that we just forget about for now, because it doesn't depend on the parameters, because we assume it's fixed because we have the identity covariance matrix. If we then compare these two expressions right here, then we see they're actually quite similar, because this is my encoder. So what I do in this loss is I take my x, then I encode it, then I add some noise. This is a reparameterization trick, and then I decode it, and then I compare it to the x. So the only difference is actually that I have this Gaussian noise here. I have an additional term over here. I have this regularization term. That's also not in the autoencoder. And this one is just ensuring that when I encode stuff, then on average it looks like a Gaussian distribution. So I can really view as a VAE as an autoencoder, where I got instead of having a deterministic encoder, then I got this noisy encoder. When I encode stuff, then I add noise. And then I also have a regularization of the latent space. So it means that with a regular autoencoder, then whenever I encode stuff, I'm free to place it anywhere in my encoding space or latent space. Whereas the VAE says, oh, you should preferably place things close to my prior, my Gaussian prior. If you place things far away from the Gaussian prior, then you're penalized by this KL term. The nice thing about the VAE is that we get this stochastic latent representation. Just like in autoencoder, we can actually take things. In this case, it's a model trained on MNIST, and then I stochastically encoded the digits in MNIST, and then you see that this is my latent representation of MNIST, and then this is color coded according to the different labels. And when we get this nice clustering in the latent space. And in fact, if you this is another view where I say, oh, if I take these ones down here, you can see that this part of the latent space is reconstructed to zeros. This part up here is reconstructed to ones, and so on. So a nice thing with this type of deep generative models is that we get this latent representation of our data. That can be useful. I'll talk about that in a couple of slides for downstream tasks. And I also want to mention, because we're going to talk about that in a couple of slides, what I'm showing here is actually that I take each of my for instance, test data or my training data, and then I encode it, stochastically encode it, and this distribution I get out by taking my full data set and stochastically encode it, that's what's called the aggregated posterior. Okay, so what can we use VAEs for? So we can, of course, use them as data generators. So we can use them for generating pretty images, like we talked about in the beginning. But we could also use them for data augmentation. So if I want to train a classifier, I got a small data set. For instance, I got an underrepresented class that I want to do classification on. Then I could train a VAE, and then I could use it for generating more training data. We can use that as a density model. That could, for instance, be that it could be useful for doing missing data imputation. So if I got a data set where there's some missing values, I could train a VAE on it, and then could use the VAE to impute the missing values. I can use it for data acquisition. So assume that I got some setup. It could be that I have some patients that are coming in. I already have some observational data of a lot of patients coming in, and then I want to figure out sort of which variable is which information is the most useful to acquire about this patient. Do I want to do a blood sample of the patient? Do I want to do a hearing test, and so on? Then I can, because if I do like a joint model of all variables and all tests I could perform on a patient, then I could sort of use the sort of set up an algorithm for using VAE to do sort of sequential variable selection. So what variables should I acquire from this patient to come up with a diagnose? And then we can also use it for dimensionality reduction. And we basically, or representation learning, and basically just like we use PCA to visualize high dimensional data sets, we can also train a VAE, and then we use the latent space to do data visualization. But we can also use it for semi-supervised learning. So if you got a lot of unlabeled data set, and you got like a huge set of unlabeled data set and a small labeled data set, then we can first train a VAE on the large unlabeled data set. And then afterwards, then we can use this low-dimensional latent representation to train a standard supervised model. And that way, we can utilize a large unlabeled data set to learn a good low-dimensional representation. So imagine if you got a very high-dimensional data set and very few samples, then it would be very hard to fit fit a classifier on it. But if we can project that in a smart way into a latent space, then we can train a simple classifier. So if we go back to this, if we go back to this example here, like we can do this unsupervised here. I can train this model unsupervised on MNIST without knowing the classes. And if I give you this plot right here without coloring it, but tells you that a 0 is placed down here, and a 1 is placed up here, and a 2 is placed over here, then with very few example points, this latent space, you could construct a pretty good classifier. Do you see that? Because you actually see that you already you got a two-dimensional space where you got a fairly good separation of the classes, right? Yes?
In the next slide, for which of these uses could we accomplish the same thing with a non-variational autoencoder, and when we choose to use this?
So your question is you could do like this part here. You could also do that with a non-variational autoencoder, right?
Space, like learn it, however, just with like a GAN or that sort of.
Yes. So you could yes. So one thing, if you just learn it with another way of doing this, you throw away some uncertainty you got about the latent representation. So there's definitely the cases where you like if you just use a standard VAE, then you just get one latent representation. Whereas here I actually get a distribution over my latent space, which I can use downstream to sort of say how certain am I about this classification. Yes, but there's fixes for that, and we're going to talk about that in a couple of slides, because there's issues with compressing it into this Gaussian distribution, but there's fixes for that, and we're going to talk about that in a couple of slides. And there's also another thing you can do in the variational setup, is that instead of doing this as a two-step a two-step semi-supervised learning, where you first learn the VAE and then use the latent representation, you can also cook up a model where you have all the variables in the same model, and you can really see this, but the idea is that we got the unobserved latent variable, then we got the observed x's, and then we got a partially observed model. So we can actually train a single model that's doing semi-supervised learning, where we say sometimes we observe the label and sometimes we don't observe the label. And the nice thing is, if you do this, then you get a full generative models, and then you can do all the types of probabilistic queries we talked about in the beginning. You can use it for doing classification. You can also say, given a label, what's the most likely image, and so on. So we can do all these nice queries we can do with generative models. Okay, so one thing I want to ask you. Oh, sorry. That was too much. So VAE spatial. I flicked. Okay, so I already gave away the answer. So if you read online, you'll see many people say, "Oh, you got variational autoencoders." Because you hear this variational thing and you talk about this prior, you would say, "Oh, it sounds like a Bayesian model." And VAEs are inherently non-Bayesian models. They just borrow a lot of terminology from Bayesian inference. So why are they not Bayesian? So we learn the model by approximate maximum likelihood. That already tells you this is not a Bayesian model. If we do maximum likelihood, then we're not Bayesian. Like if we want to be Bayesian, then we want to calculate a posterior distribution over our parameters. The prior is not a Bayesian prior. So we don't update it. If we have a prior, if we're Bayesians, then we put a prior on our parameters, then you observe some data, and then we update our belief about those parameters. Here, at least, we're going to talk about later that we could learn it using maximum likelihood, but in the basic setup, we start with a Gaussian prior, then we train the model, and then when you generate afterwards, the prior remains Gaussian. Also, the posterior, if you look at this posterior, then you can ask, you have this posterior distribution, you have the P of Z given X. And again, that's not in the sense that we update our distribution. This is for a single data point. And the way you can think about this posterior is just like the component responsibility in a mixture model. So it's basically I take one data point and then I say, you know, in a mixture model, you say, if I use a mixture model for classification, I take a data point and then I say which of sort of the mixture classes is this point most likely to come from. And this posterior also tells me which part of the latent space is most likely used to generate this data point. We can make Bayesian VAEs, and people have done that. And the way you'd make a Bayesian VAE is you would put priors on the parameters of the model. So for instance, you could put priors on the decoder parameters. But as they are just frequencist models we learned using maximum likelihood. How are we doing time-wise? I'll talk for about 10 minutes more. I know it's sort of a long stretch I'll just take your questions. It's a long stretch with a 1 hour lecture, but then you have half an hour where we'll do exercises and you also use that for a break.
Yeah, I'm really curious. So have people found these Bayesian VAEs useful?
That's actually a very good question. We also played around with them. And it turns out, at least in our experiences, that it's actually being Bayesian about the parameters is actually detrimental to the generative performance of them. But people have found settings. They are better for if you want to do out of distribution detection. There's some papers where it actually increases the out of distribution detection performance. We looked at them in a setting where we sort of want to sort of model stability of proteins, and they're actually also better models for stability of proteins. But in general, it's actually an open question a bit. How useful Bayesian VAEs are, and how we can make them more useful. But there's also some issues with standard VAEs I presented so far. One of the sort of issues that you often see is what's called posterior collapse. And that's basically that the decoder can learn to ignore the prior. So if you think for a non-trainable prior, for instance, a standard Gaussian, then one way to minimize the regularization term over here, that is if I take my variation distribution and just ignore the x and say no matter what x I put into my encoder, then you always return a standard Gaussian. So if you just ignore it and say my variation distribution is always a standard Gaussian, then you actually minimize this term here. And in fact, if you have a very powerful decoder, it could be an autoregressive model like an LSTM, then it can happen that this model just learns I don't need to use sort of the prior sample. And that's a local minima for the elbow. Just learn, I just encode everything to a standard Gaussian, and then once I've done that, then I just focus on getting good reconstruction with ignoring the label. And that's usually a local minima. And one way we can address that is, for instance, by warming up the KL terms. The idea is that we start by multiplying the KL term by 0, and then during the training, then we increase the weight of the KL term until we weight it by 1. A second issue is what's called the hole problem. And that's when you have a mismatch between the prior and the aggregated posterior. You already saw an example of the aggregated posterior. The aggregated posterior is just if I take my data and then I just encode it and think about it as a mixed distribution. And that could look something like this. Over here, I got my prior here in yellow, and then I got my aggregated posterior. It has this star shape over here. So you see there's these holes in between the arms of the star. And what happens if I then afterwards sample from these holes here, then I get sort of unrealistic sets according to the model, and then I get low quality samples from my model. And the last issue that I want to highlight is that if you think about if you have a continuous deep latent variable model of VAE, so for instance with a Gaussian output, then it actually just like for a Gaussian mixture model. Hopefully some of you heard this before. If you take a Gaussian mixture model, it's actually ill-posed to say I want to do maximum likelihood in a Gaussian mixture model. There doesn't exist a maximum likelihood estimate for a Gaussian mixture model because the likelihood is actually unbound. You need, if you want to do in fact, if you really want to do Gaussian mixture models, you need to either regularize them or you need to be Bayesian about them. And it's the same is true with the VE. The likelihood for instance, a Gaussian output is actually unbounded. And if you just sort of try to maximize it wildly without regularizing them, then it's actually detrimental to generalization. So it actually turns out you also end up getting very bad samples. Even though you have a super high likelihood, you actually get very bad samples. And the solution is that you need to regularize if you're in the continuous case, you need to regularize your network, or you need to clamp the variance to say there's a minimum variance, or you need to be Bayesian about the covariance of the output. So there's many ways of improving VAEs and also addressing the issues I just talked about. The things we can improve the prior, we can improve the way we do inference, we can do something else than variational inference, we can use these importance weighted bounds instead. We can also use more expressive variational distributions. Because of time issues here, I'll just focus on how we can improve the prior. If you want to read more about how you can improve inference or how you can improve the variational distribution, then I recommend reading more in Jakob's book on deep differential modeling. Okay, let's talk about how we can improve the prior. So we look at the standard elbow, and then let's look at the expected value of the regularization term, so the KL term over here. If I take the expectation of the KL term with respect to data, then it's fairly simple, but let's skip the details how we do the rewriting. But it's fairly simple to do the rewriting. You can write the KL term in terms of a cross entropy between Q here is the aggregated posterior, so this thing where I just encode my data set. So cross entropy between the aggregated posterior and the prior. And here I put a parameter on the prior because we're going to talk about how we can learn the prior. And then I also have the expected value of the entropy of my variational distribution. So this is just an illustration of if you look at this first term here, then what we see is this whole problem where this is my prior over here and this is my aggregate posterior. And it turns out that difficulties in optimizing this cross entropy, that's actually what leads to these holes in the prior, because it's hard to minimize it's actually hard to get an aggregate posterior that fits with my prior assumption. Just like you said, it's hard to take my data and compress it into this into this assumption of being able to compress the prior into a Gaussian. So what happens is sort of try to illustrate it here. We got this term here that says, oh, we should have maximal entropy for our variational distribution, which means that it should be as wide and as flat as possible. And at the same time, we also, this term here says, oh, but it should also match a Gaussian. And these competing interests, in particular matching this one, turns out that it results in that we're getting these weird holes in our aggregate posterior. And this can then be addressed by learning a prior. So instead of having this Gaussian assumption of prior, we could actually say, oh, why don't we just learn a prior, something that's not Gaussian. And if you see here, in fact, the way we could actually minimize this cross entropy would actually be to say, oh, our priors, in fact, are aggregated posterior. So so probably the best prior in terms of the cross entropy would be this aggregated posterior, because it minimizes the cross entropy. And we could actually use this as a prior, but it's not feasible for, if you have a lot of data points. Because if we train a million of data points, then we suddenly got aggregated posterior that's actually a mixture of a million distributions. But we notice that this is a mixture distribution. So I could say, oh, couldn't we use some mixture distribution as a prior? And in fact, we could use a mixture of a Gaussian as a prior, where we say, oh, let's use the number of components that's much less than the number of data points. And for instance, if we think about MNIST, where we got 10 classes, then we could say, oh, we actually already know that there's 10 classes in here, so maybe it could be a good idea to use a mixture prior where we've got 10 different classes, because then we could actually use it for doing unsupervised clustering of our data. So the setup is basically that we say our prior is just a standard mixture of Gaussians, so it's a weight here that needs to sum to 1 and be non-negative, multiplied by a number of Gaussians where the learnable parameters are the mixture weights, the means of our Gaussians, and then the variance or the covariance of the Gaussians. And typically, we just use a diagonal covariance matrix here. And if we do this is an example from Jacob's book where we learn as like a low dimensional version of MNIST. This is what a learnable mixture of Gaussian priors looks like. So you got the prior here in greenish in the background, and you got the aggregate posterior. And we already see it's not a perfect match, but we to aggregate posterior, but we see we get a much more sensible prior than compared to the standard Gaussian prior. Of course, this introduces a new latent variable because you can think about the mixture component as a latent variable, but we can actually just implement it by doing this full sum and then just learn these mixture rates by using stochastic gradient descent. And this actually, if you use a mixture of Gaussian priors, then we can do end-to-end clustering with VAEs, because then we can learn this mixture prior, and afterwards you can say which component were you most likely to come from in the prior. You'll try this later in just a few minutes in the exercises. We could actually also use something that's closer to the aggregate posterior. We could use what's called a variational mixture of posterior prior. So it's improvement over the mixture of Gaussian prior, and the setup is that we use this mixture model where we say, let's take the variational distribution, and then instead of evaluating variational distribution in every data point, then we just pick a number of pseudo inputs. So we pick k pseudo inputs that are much less than the number of training points. And then we learn those pseudo inputs. They will be the learnable parameters. So it means that we place some pseudo inputs. We move around and say we model our prior as a mixture where we mix the variational distribution in a number of pseudo points. And this improves the quality of the model even further. You get fewer holes. And this is an example of, again, the same data set as before here. Where we learn this VAM prior, as it's called, and you see here again you get a much better fit between the aggregate posterior and this VAM prior. One of the challenges here is initializing these pseudo inputs. So you need to initialize in some data points. It's sort of the same challenge as when we also know it's challenging to initialize a mixture model. So you need to sort of make sure that you have the pseudo inputs distributed far away from each other. The last thing I want to talk about is hierarchical prior. So another way where we could choose a more flexible bias, we could use some inductive bias. And inductive bias we commonly use in machine learning models is that we assume that our model is hierarchical in some way. For instance, when we build deep neural networks, we also assume that sort of a hierarchy in feature extraction, that we extract low-level features first, and then later on we extract high-level features. And we can construct VAEs where we have a hierarchy of latent variable model of latent variables. And this is the graphical model for it with two latent variables. So the idea is that we have a latent variable that we use to generate the next latent variable, and we can sort of extend this hierarchy. And in the end, then we generate our data based on the latent variable lowest in the hierarchy. And then you end up with a model that looks like this. So we have this factorization where we assume its factors as P of Z2, P of Z1 given Z2, and then P of X given Z1. So we don't assume there's any connections from the upper latent variables to the data. And a natural variational posterior is just to choose one that's buttoned up. So the way that we encode data is that we take our data and then we encode it we have a stochastic encoder that encodes it to Z1, and then a stochastic encoder that encodes Z1 to Z2. One issue with that is that we easily get posterior collapse. So it's easy for the model to learn to basically just minimize this KL term by saying that when I encode Z1 to Z2, then I just basically just ignore the value of Z1. Because one thing that, of course, would minimize this one is just assuming that Q of set 2 given set 1 is just P of set 2, that we don't use the information. And you can sort of imagine if you build this big hierarchy, then if you look at sort of the lowest part of this model, if I just look at set 1 and X, this in itself is just a standard variation autoencoder. So we know that this is already a quite powerful model. And if you have like a 32-dimensional latent space and we train this on MNIST, then this in itself can actually capture MNIST. So it sort of will say, oh, I don't need this part because I can just model everything just using the lowest latent variable. Lowest latent variable. So one thing you can do that is that instead we can write the variation posterior top down. So we write a variation posterior where we sort of got a deterministic part where I input X into my neural network, I get out these sort of intermediate latent variables, and then stochastically I decode by first sampling I stochastically encode by first sampling set 2 given X, and then I sample set 1 given X and set 2. And turns out if we do it this way, and then what people do in practice is they actually share that they actually use the decoder in the encoder over here for the variation posterior. That helps preventing posterior collapses, and that's how people typically train hierarchical VAEs. And then they also use this warm-up where they gradually turn on the KL terms to avoid posterior collapses. So these are state of the art I just want to show this drawing also. So this is what you end up with sort of in the hierarchy. If I sort of do show the aggregated posterior for the hierarchy, then you see what happens is that we got something down lowest that doesn't look super Gaussian, and then as we encode things, then we end up with something that looks super Gaussian at the top of our hierarchy. And we also sort of see this nicer split between, this is also MNIST between MNIST. So this is the state of the art. You can do these very deep VAEs. This one is with 48 layers on high quality fashion. On high quality Celeb A, I think. And then you get these super photorealistic images. All right, I've been talking for an hour now. I'll just sort of say the takeaway about deep latent variable models is that deep latent variable models is a powerful framework for building generative models. And I want to sort of stress this, that what I call a VAE, that's a deep latent variable model learned with amortized variational inference. It allows for representation learning, as you saw, and we can also use them, for instance, for semi-supervised learning. And the key component we can improve is the prior, the inference, and the variational distribution, and we focused on improving the prior. So we're going to take half an hour now where you work on this first exercise about variational autoencoders. There's a Jupyter notebook. There's a link here where I got it on GitHub, but you also put it on sort of the course, the ProbAI. Yes. Where there's a link that will take you directly to a version in Colab. So it runs on Google Colab, but you can also run the Jupyter notebook locally. The idea is that there's 3 exercises in there. The first one is just about understanding the code. So you looked at a Pyro implementation of a VAE yesterday. This is a pure PyTorch implementation using torch distributions. The idea is the first exercise is understanding the code. Oh, there's a spelling error here. Exercise 1, 2 is about calculating the test elbow and then try to plot the aggregate posterior. And exercise 1.3 is about implementing a mock prior. And I don't expect you to get here, but then do the exercise afterwards. I think it's more realistic that you get through the 2 first exercises. But we'll do that until 10:40. And then at 10:40 we'll start talking about flows. So and there's TAs moving around helping you with the exercises. Any questions before the exercises? Good. Then let's do the exercises. I think in the interest of time I'll sort of continue talking, and then the TAs, you will be around, right, to answer more questions regarding the exercises. Yes, and then I'll move on to talk about normalizing flows. Otherwise, I'm afraid we'll run out of time. Okay, so the second class of models that I want to talk about is the class of that's called normalizing flows. So idea in flow-based models, we're going to talk about that. It's sort of slightly related to VAEs and in some sense not related to VAEs. The idea in flow-based models is, imagine that we have a normal distribution like this. This is just a two-dimensional normal distribution. Could I then sort of take this normal distribution and sort of mold it into a different distribution? Think like, you know, like a ball of modeling clay. Could I sort of push it in different directions, stretch it in other directions to get out a different distribution? And that's the essential idea in flow-based models, is that I take a normal distribution, then apply some function, I could sample from it, then apply some transformation of the sample, so transform it into a different distribution. In this case, I sort of pushed on the sides and stretched it out in the corners like this. So the generative process in a flow is essentially just that we pick some, in this case it's called the base distribution, then we sample from the base distribution, apply some transformation, and then we get out our x. How is that different from a VAE? This was the generative process in a VAE. We sample the set, we apply some function to the set, and then we sample the set from the P after. What's the sort of the essential difference here?
You have only one source of noise or variability, which is in the base distribution, sampling from that.
Yes. So what you said, we only have one source of noise. Exactly. So here we got two distributions in play. Here we only have one. So in this case, we sample from the base distribution, we apply the transformation, and we directly get our data point. Whereas here we sample from, it's called the prior for the VAE, then we get out parameters of our output density, and then we take those parameters, put them into another density, and then we sample our data points. So it's sort of this, in some sense, is this P here, there's a difference between the two types of models. So if we want to calculate the density of the x here, then we need to apply the change of variable formula for probability densities. And this requires that f is invertible, so it's a bijection, and it also requires that is differentiable. So it's a bijection basically means that there needs to be a one-to-one correspondence between the U space and the X space. And if there's that, if there's that, then we also have an invertible function, and then we also require it to be differentiable. So in the case of a VAE, then we had that the dimension of the latent space is lower than the dimension of the data space, and therefore f cannot be a bijection. We cannot have a bijection between these two spaces. Whereas for flow-based models, we will have the requirement that we need the dimension of the two spaces to be the same. Otherwise, we cannot have a bijection between the spaces. This is hopefully a well-known example of something that you could actually consider to be a flow model. So let's assume that we have that U is just lying on the real line. We assume that P of U is a normal distribution, and then we assume that our transformation is just 2 times U plus 1. So what would be the density of X then? Yes, I heard somebody saying a normal distribution, and what would be the mean and the variance of that normal distribution? Yes, mean 1 and variance 4. That's correct. So density is a normal distribution with mean 1 and variance 4. So basically just, we actually took this standard normal distribution here, and then we transformed it into a normal distribution with the shifted mean and a higher variance. So that's actually a very simple example of, we could consider this to be a very simple example of a normalizing flow. How do we actually get there? we actually use this change of variable formula for scalar densities. And it looks like this, that if I want to know P of x, then I take P of u, and then I multiply by du dx. And if I want u, then I need to, if I know the x and I want u, then I basically have to take, I have to invert this one, so I can get u by applying the inverse transformation here. So P of u, I have to evaluate that in the inverse, when inverse the transformation evaluated in x, and then du dx, that's basically the derivative of the inverse function. So we can actually write this down. We have that the inverse here is fairly easy to calculate, right? We subtract 1 on both sides, and then we divide by 2. So this is the inverse function. And the derivative of the inverse function is also fairly easy. If we take the derivative with respect to x, then we of course get a half. And then you just plug this into the change of variable formula. So I need to evaluate P of u in x minus 1 divided by half. So that this was this guy here. And then I need to multiply by the half here, right? That's what the formula tells me. Then I plug this into the standard expression for a standard Gaussian. So I replace the u here with this expression here, and then I multiply by half, and you see that this is exactly a Gaussian with mean 1, the mean up here, standard deviation 2, and this half here is exactly fixing the normalization constant. So you can sort of view this absolute value of the u dx as the quantity that's sort of making sure that we get the right normalization constant. All right, so I just want to mention that if some literature and for flows, I would also recommend Jakob's book here, and I would definitely also recommend this review here by these guys from DeepMind on normalizing flows for probabilistic modeling. And the reason why I'm mentioning it now is that I'm following the notation of this paper. So if you want for reference for the rest of this lecture, then go look in this paper here. Okay, so the basic setup of a normalizing flow is that the generative model can be described in the following way. We assume we have two random variables, u and x, that's lying in d-dimensional space, and then the generation is driven by the model that I sample u from what's called the base distribution, then I apply the transformation, which must be a diffeomorphism, meaning that it's invertible and both t and its inverse must be differentiable. Then I apply this to the sample, and then I get out x. And usually we say that P of u, this can be a fixed base distribution, but it can also be parameterized by phi, and t is parameterized by psi. Sometimes I leave out the parameterization just to simplify the notation. And then the density of x is given by the change of variable formula, which in multi-dimensions looks like this, that P of x is equal to P of u, and then instead of just taking the differentiable, we will take the determinant of the Jacobian of the transformation evaluated in u, and then we take the inverse of its absolute value. And recall that the Jacobian is just a matrix of all the partial derivatives. So in the first row, we got the partial derivatives of the first output of the transformation with respect to all the different inputs. Then in the next row, we got the second output up until we have the dth output. So remember that this transformation goes from RD. Why is that not on the slide? It goes from RD to RD because it's bijection. So you input a vector into the transformation, and the value of the transformation is also a vector. And a nice thing is that is actually this formula, if we know these terms, we can actually evaluate it. So it means that compared to the VE we just talked about, where we cannot evaluate P of x, in this model, typically for flows, we can actually evaluate the probability, which means that they are at least in some cases, exact likelihood models. Oh. Okay, let's just look a bit more at the Jacobian. So we have what's called the inverse function theorem that tells us that the Jacobian of the inverse transformation is equal to the inverse Jacobian of the transformation. That gives us that if we want to write this change of variable formula, we can either write p of x as p of u multiplied by the absolute value of the inverse of the determinant of the Jacobian, or we can also take the determinant of the Jacobian of the inverse transformation. And then we also use that if we take the inverse transformation and when take the determinant, then we can just pop the inverse outside. And this is the absolute value of the determinant of the Jacobian. You can think about that that's quantifying the relative change of volume around u due to this transformation. If it's equal to 1, then we say that the transformation is volume preserving, and this could be an example of a volume transforming transformation. If I take a volume, if I look at this square and see how it's transformed with a volume transforming transformation, this could be an example where we basically just shift the space. Then I get out in this case, I actually get out a square with the same volume. You can also sort of think about that if you got a value that's smaller than 1, then you're shrinking the volume, and if you get a value of the absolute Jacobian, the larger one, then you're expanding the volume around you. Okay, I just want to take another simple, hopefully well-known example of something we can view as a flow, and that's how many has heard about the inverse transform sampling. Okay, so there's a few in here. It's a general algorithm for or procedure from sampling from an arbitrary probability distribution. So assume that we got some probability distribution, and it could in principle be any continuous univariate probability distribution. And the way and assume that we want to sample from this distribution. If we want to sample from this, then we can usualize the cumulative distribution function. And remember that the cumulative distribution function is just if we integrate our function from -infinity up to x. So it's basically if I have a normal distribution here, then this is the cumulative distribution function. So for instance, if I ask what's the cumulative distribution function at z, then it's how much probability mass do we have under the curve up until x equal to 0. So it means that if I want to evaluate the CDF in 0, then I integrate this part, and that corresponds to this point here, that the integral up until 0, that's half. That's also the middle of the normal distribution. And so this inverse transform sampling, one way of sampling from this distribution is that a general procedure for that is that we sample a uniform between 0 and 1. So we sample a uniform value here on the y-axis, and then we usualize the inverse CDF. So if I want to sample from a normal distribution, I can sample a value uniformly here on the y-axis, and then I can map it back to an x by using the inverse CDF. So for instance, if I sample a half, then I would map it back to 0. There's also an illustration of it here where I say this is the CDF of a normal distribution. I sample uniformly, and then you see what I get out here is samples from the Gaussian if I use the inverse CDF of a normal distribution. So you can think about this as a flow where the base distribution, it should have said P of U here. The base distribution is a uniform distribution, and the transform is the inverse CDF. And this, if we assume that the CDF is invertible, and then we can actually transform a uniform distribution to any distribution that has an invertible CDF. So this actually tells us that a flow can represent nearly any distribution. Because as long as the CDF is invertible, then we can, in the one-dimensional case, then we can take and transform a uniform distribution to whatever distribution that we specified a CDF for. And you can make a similar argument in multiple dimensions. So that tells us that a flow is nearly a uniform distribution approximator. With sort of we need to be able to that the CDF is invertible. Otherwise, we cannot transform a normal distribution into the distribution. Okay, so how do we then? So far we just talked about normalizing flow. The next question is, of course, how do we learn them? We want to be able to learn the parameters of the transformation and possibly also the parameters of the base distribution from data. So the principle that we're going to apply is what we already talked about multiple times, is we're going to do it using maximum likelihood. So given some observations, then a natural objective is the log likelihood function. And the log likelihood function is just the sum of the log probability of our data points. And for the flow, we would write log p of x, and then we just plug in sort of this transformation we already looked at. So what it looks like for flow is it's the log probability according to the base distribution, and then we apply the inverse transform to our data point, and then we need to, because we're in log space, then instead of multiplying, then we'll add the log absolute value of the determinant of the inverse transform. So we would like to find the maximum likelihood estimate, and that just means that we would like to maximize this expression with respect to the parameters of the transform and the parameters of possibly the base distribution. So we can just do this using stochastic gradient descent as we would normally use with neural networks. But in order to do that, then we need to be able to evaluate, of course, the inverse transform and its log Jacobian and the log Jacobian determinant. And of course, we also need to be able to evaluate the base distribution, but usually we will pick a fairly simple base distribution. And of course, we would also need to be able to calculate their gradients. And one note here is that if we want to use MLE, then we just need to know the inverse transform and the Jacobian of the inverse, or possibly just the Jacobian of the transform. We actually don't need to know T, so we can people actually use that in construction of these transformations. The T is only needed for sampling. When through the sampling procedure, there we need to know T, but for maximum likelihood, it's important that we know the inverse transform to be able to calculate maximum likelihood estimate. So we would usually use a standard Gaussian for the base distribution, but we would like to have a flexible transformation. And sort of in the age of deep learning, we would of course like to use a neural network. But there's an issue. How do we specify a neural network where the function is invertible and the log Jacobian determinant is easy to evaluate? That's not fulfilled by standard feed-forward neural network. If I just initialize a random initialize a neural network, I'm definitely not guaranteed it to be an invertible function, and I'm definitely not guaranteed that I can easily evaluate its log Jacobian. However, one thing we can do is that we can formulate very simple neural network-based layers that fulfill these criteria. And then we can stack very simple layers, just like we stack simple transformations and deep neural networks. And then we can get expressive powers by stacking many of these networks. Remember, in a standard neural network, each layer is just a linear transformation and a non-linearity. And then if we just stack enough of them, then we get expressive power. And sort of the same idea that you use in flows. So the idea is that we are going to construct this transformation by simpler transformation. So basically just doing a big function composition. And the nice thing is that if each of these, you can show that if each of these transformations fulfills the properties that they are diffeomorphisms and the Jacobians are accessible, then this composition is also a diffeomorphism, particularly it's invertible, and it's also easy to calculate its Jacobian. And if we specify it this way, then we can iteratively evaluate both the forward and the inverse transform. So if I want to evaluate the forward transform, then I basically just keep iterating that I start with a U, then I evaluate T1, then what comes out of T1, I put that into TU, and so on. And same with the inverse. If I start with an X, then I can apply the inverse transform of the X, and then I can keep just iteratively applying these transformations. I got an illustration on it on the next slide. And the nice thing is that if I look at the log Jacobian of a composite transformation, then I can use the chain rule for Jacobians. And what the chain rule tells me is that the determinant of the Jacobian is actually of a composite transformation is just the product of the determinant of Jacobians of each of the transformations. So I just calculate the determinant of this Jacobian, of the next one, and so on, and I can multiply them together, and then I can just move the swap, exchange the swap and the product. So it's just the sum of the log determinant of each of the transformations. So here's another illustration of it. So the idea is that if I got this sequence of transformations where I'm starting, that let's just call U for Z0 in this case. So I'm starting with my base distribution, in this case Gaussian. If I got a sequence of transformation and composite them into a single transformation, then I can just apply my first transformation, then I get out Z1, then apply my next transformation to get out Z2, and I can do that all the way for all the set transformations, and in the end I get out my X. This is an example of sequentially applying transformations to a Gaussian where I end up with this star-shaped transformation. And the nice thing is that if I want to calculate the log determinant Jacobian of this full transformation, then I can just calculate the log absolute determinant of the first transformation, and then I can add the log determinant Jacobian of the next transformation evaluated in this set 1 after applying the transformation and so on. I just keep evaluating these and summing them together, and then I get the log determinant of the full transformation evaluated in my starting point. Does that make sense? So the nice thing is that it's actually with normalizing flows, it's actually very simple to construct composite transformations if each of them fulfill that. It's easy to if each of them fulfills that they're invertible and a bijection, and each of them have the property that it's easy to evaluate the log determinant of the Jacobian. And of course, if I want to go the opposite direction, then if this one is invertible, then I can just start with my set K, evaluate the previous one, and so on. And once I evaluate all of them, then I can just fill out this formula. So why is it called a normalizing flow? So the flow part of normalizing flow refers to the sequence of transformations. that basically you can think about that a data point is flowing through the sequence of transformation. The normalizing part of normalizing flow refers to the reverse flow, where a data from this complex distribution flows back to a Gaussian distribution or a normal distribution. So you can think about that the inverse transformation is normalizing our data in the sense that it's taking our complex data distribution and transform it into a normal distribution or a standard Gaussian distribution. So that's the reason why they're called normalizing flows. The question is, how do we then construct these transformations? Now we know that if I just can construct transformations that fulfill these properties, then I can stack them together and get a complicated transformation. So we want to construct, we still want these transformations to be somewhat powerful, and we also want them to be nonlinear in some sense. So we want to utilize a neural network to construct a transformation that's invertible and where the Jacobian is easy to evaluate. And there's many ways that you can construct these transformations, but we're particularly going to look at what's called the affine coupling layers combined with permutation layers. The idea with the affine coupling layer is that imagine that I have a vector set that I want to transform into set prime. The idea is that, and assume that it's a capital D-dimensional vector. Then I take the first D dimensions of my vector, and I don't do anything with them. I just have the identity transformation. So the input to T is just set 1, and I just output set 1. So set 1 prime is the same as set 1. Then for the remaining variables, I just do an affine transformation for them. So that means that I just, so tau here is affine transformation. So I just take set D, D plus 1, and I multiply it by value, and I add a value. That's affine transformation. But the parameters of the scaling and the translation, those are neural networks. So I take set 1 up to set D, I put it into, in this case, it could be one neural network, but let's call it 2 neural networks, a network called S and a network called T. And those networks then output how should I scale set D plus 1, set D plus 2, and so up to set D, and how should I translate them. The nice thing is that if I construct it this way, then the inverse, if I look at the inverse here, for the first D variables, the inverse is easy to calculate, because that's just the identity function. We know that one is invertible, right? So that part is easy to invert. So if I want to calculate the invert, I can just take the D first variable and just copy them down here. Once I invert the first D variables, then I can calculate the scale and translation. And as long as the scale is non-zero, then we know our affine transformation is also invertible. And that means that I can calculate the inverse transform, and then I can apply that to the rest of the variables. So affine coupling layers, they were introduced by Ding and al, and they are a key component of the real NVP model. So if you write it down, mathematically, what I just had in the drawing before, then we have a transformation that first partitions the input into the first D variable and the last D minus capital D minus small d plus 1 variables. For the first part of the transformation, then that's just the identity function. That means that the output is just equal to the input. And for the second part of the transformation, we are applying this affine transformation. And the idea is that S and T here, they can be arbitrary neural networks. So I take this set here, I put it into a neural network, and then what I get out of this neural network, I put it through the exponential function. That's just to ensure that the scale is non-zero. And then I do element multiplication with the output of this neural network with the remaining set variables. And then I add the translation here with also an arbitrary neural network. And there's no restrictions on these neural networks. They can be any networks, and we still end up with invertible transformation. So just to recall, this just means that, just as I showed, it means that for any of the first the first D i's, I just copy over the exact value, and for any of the remaining ones, then this network out here, this network output is like a multi-output neural network, and I take out the ith value. So it's just a scalar I get out here to scale the ith value, and then I just have a scalar here. So I also pick out the ith value of the translation network. So since it's an affine transformation, it's easy invertible. So if I want to calculate the inverse, that was just sort of here. I basically just swap around set and set prime, and for this one. It's also easy to invert. So you can just say if I want to invert this formula right here, then I subtract the translation on both sides. That gives me this equation here, right? So it gives me set prime minus the translation is equal to the exponential of the scale network multiplied by set D, and then I divide by the scale on both sides. And if I divide by x, that just corresponds to saying minus the value inside. So I end up with this formula right here. So it's very easy to invert. It turns out that for the affine coupling layers, it's also very easy to calculate the Jacobian. So let's try to write the Jacobian on the following block form. So I can write, so these are all matrices in here. So I can say, what is the Jacobian, where it say, sort of, where I look at all the partial derivatives with respect to the first D outputs, of the first D outputs with respect to the first D inputs. This one down here corresponds to all the partial derivative with the last outputs, of the last outputs with respect to the first inputs. And then these are the cross terms. So this one is the partial derivatives of these guys with respect to these guys down here. And this is the partial derivative of these guys up here with respect to these guys down here. So let's start with the first one. So this start with this one up here. So this is the easiest one. So this is just the partial derivative of these guys with respect to these guys. And since this is just the identity function, it's very easy to see that on the diagonal, then we have that set one. Oh, there's missing the primes on up here. This should of course be set one prime respect to set one. This partial derivative is of course 1 because it's just copied, whereas all the remaining partial derivatives in this row is 0 because, for instance, this one doesn't depend on the value of this one. So it just end up with identity matrix for this partial derivative. Similar, another one that's easy, and we're also missing the primes up here. These should be primes. So the partial derivative of these guys here, so the first D variables with respect to these ones over here, that's just going to be, they're all going to be 0. Because the value, this value is identical to this value, meaning that the value of set 1 prime does not depend on any of the values over here. So this is just going to be a big 0 matrix. Those two blocks of the Jacobian. Now let's take a look at this Jacobian here. So this is the partial derivative of these guys here with respect to these guys down here. What is this block Jacobian? So try to just discuss with the neighbor for a couple of minutes what this block Jacobian should be. All right, so I'm going to interrupt you now. Any suggestions for the off-diagonal elements? So any suggestions? What are the off-diagonal elements of this Jacobian? Yes, there you go. There's 0. Yes, and that's because if for instance, if I look at this guy over here, then the value of this guy doesn't depend on any other values than it doesn't depend on this guy. It only depends on this guy over here, and it depends on these guys over here, right? So. And all the off-diagonal element, all the off-diagonal elements in this block matrix is saying, you know, how does, for instance, this one depend on all these in this partition? That's not itself, right? So you see that the variable, any variable up here, only depends on its the same variable's input value, and then these values over here. So all of the all the off-diagonal elements are 0. What about the diagonal elements? What are they?
Exponential of length.
Exactly. All the diagonal elements are just the scale factor right here. Because if I take the partial derivative of, for instance, if I take the partial derivative with respect to set I, right? Then the partial derivative with respect to set I is just the scale factor right here, and the partial derivative of this guy is 0. So I get a diagonal that's exactly just this one should of course, sorry, there's a couple of mistakes here. This one should of course say D plus 1. So it's just all the scale factors on the diagonal, and all the diagonal elements are 0. So another way of writing this matrix is also say it's the exponential of the output of the network, and then this diagonal operator that turns this vector into the diagonal of a matrix. So that diagonal matrix. So that means that now we know that this block is the identity matrix, this is the 0 matrix, and this is just the diagonal of the exponential diagonal matrix, where the diagonal is the exponential of the output of the scale network. What about this guy here? Is this guy easy to calculate?
We don't need it.
We don't need it, that's correct. But it's also not easy to calculate, right? Because this guy that's left is actually, how is, for instance, this guy up here varying with these input over here? And that would actually mean that we'd have to differentiate through the neural network. So it's not necessarily, so that this could be like a super complex derivative to take. We could take it, but it's also super expensive to take the derivative of a neural network with respect to the input. So we don't need it exactly, because this is a triangular matrix. And we actually don't care about the full Jacobian, we only care about the determinant of Jacobian. And recall that for a triangular matrix, then we have that the determinant is just the product of the diagonal. So if we want to take the determinant of this guy, it's just the product of the diagonal, and this one is just identity, so that this part of the diagonal is just 1. So you just need to take the product of this diagonal. So it's just, I just take the product of the output of the network, or I can take the x of the of the sum of the output of the scale network. So we are in a case where we can, for these transformations, we can both easily apply the transformations. They're invertible, they're fairly easy to apply, and we can also calculate the determinant of Jacobian. So this transformation actually fulfills the criteria. It's a simple transformation, right? Because it's if we look at it, this part is just the identity, and this is just a scale. But I also just said we're going to end up with very simple transformations. One issue here is that if I just stack a lot of these, right, then I would never change the first d variables, because that just keeps being the identity function. So in order to make sure that that all the variables are transformed, then we could just apply a permutation. And a permutation, that's obviously also invertible, right? So the idea is just that I could do a coupling layer, and then I could commute the variables. And it's sort of easy. This is what the transformation looks like. Sort of I transform set to set 3, for instance. I transform set 2 to set 1, and so on. And it is easily invertible, because it just sort of copy the values in the other direction. But what is the determinant of the Jacobian of a permutation? Does any try just maybe just quickly talk just for 1 minute to neighbor about what's the determinant of the Jacobian of a permutation? All right, any suggestions? Yes, so it's indeed is volume preserving, and the absolute value of the determinant of Jacobian is 1. And one way you can see that is that a permutation, that's actually just it's just a linear transformation, where you just have your you just have that your sort of your the matrix for your linear transformation just looks like something like this, where you have exactly, you have a 1 in each column and each row, right? You only have a single 1 in each column and each row. And then we can use this trick from linear algebra, that if we swap 2 rows or 2 columns in a matrix, then the determinant just changes sign. So if I say that this was my permutation, meaning that so the transformation here would be that sorry for at the first value, sort of I would that's actually it's the transformation where I say I swap, at the first value there I put x2, at the second value I put x1, and the third value I put x3, right? So that's the permutation that I have here. Then if I want to calculate the determinant of this one, then I could just swap 2 rows, right? So I could swap these 2 here, right? So I get 0, 1, 0, 0, 1, 1, then I get 1, 0, 1, and then I get 0, 1, 1. So that was an easy case, and I just need to put a -1 in front of it, because it changes sign, and then I take the determinant of this one. And the determinant of this one is easy, because that's just, I take the -1 outside, so I get minus 1 times the determinant of this guy. It's just the identity matrix, so that's just the determinant of this one is just 1, right? So I get that the determinant is minus 1, and then I take the absolute value. And I can take any of these matrices and I just sort of keep swapping rows or columns until I get the identity matrix. And depending on sort of how they're ordered, I'll keep multiplying by minus 1, so either I'll end up getting a minus 1 for the log determinant. All right, so if I actually have these two, things, then I can actually stack. I can do a coupling layer, I can do a permutation layer, I can keep stacking them, and then I get a transformation. Then I get a more powerful transformation. That's actually the idea in this one of the more famous flow methods called real NVP, so real non-volume preserving flows. So real NVP apply these affine coupling layers. Then instead of doing this permutation, then they implement in the coupling layers. They implement a partitioning of the variables based on a mask. So instead of always partitioning at a certain point, if they have an image here, they for instance do a checkerboard masking of the variables, and then they keep swapping between. Either masking out the 1, the 5, the 4, masking out the 2, 3, 7, or 8, or masking out the 1, 4, 5, and 8. So they use this checkerboard where they alternate between which variables they mask out. Then they also do some channel-wise masking, that if they got multiple images with multiple channels that they're modeling, then sometimes they mask some of the channels, and sometimes they mask other of the channels. And then they also do some squeezing of the input tensor. So they take, for instance, they take this one and they squeeze it into the having multiple channels, and then they do masking in the multiple channels. So they do a lot of tricks, but the idea is just that they actually only use coupling layers. And then instead of using permutations, they just say, oh, let's mask some of the variables, and then only feed those masked variables into the scale and translation network, and then apply it to the masked variables. There's more details about it in the notebook that you're going to do for the last part of this lecture. So the idea is that when we do sort of this random partition by masking, then we don't need the permutations. In real NVP, they also do this trick where they factor out the variables. So at regular intervals in the transformation, they say that, let's say we have, this is our image here that we want to transform into Gaussian distribution. Then they say, oh, some of the pixel values. At some point we say, for instance here, an example here, after the first transformation, we say, oh, we're not going to transform them anymore. We're just going to assume after one transformation they actually become Gaussian. So we can sort of think about that different pixels are Gaussianized at different layers. So we have in early layers, we have sort of that we sort of do the fine, like if you do it the Gaussianizing in the early layers, we can think about that sort of modeling some fine scale details of the images, whereas the one that we Gaussianize in the later layers, they're sort of modeling some more coarse grain at the more coarse grain scale, or some more abstract features of the image. So in a flow, we assume that, for instance, if we take if we take a flow like this, where we say we assume that we have Gaussian-based distribution, and then we have images as the output distribution, then we actually assume that x is a real value vector. But we know for images, they actually, we have pixel values. They can only, they're discrete values. So how can we then model an image where each pixel only take discrete values? Any suggestions? How can we sort of go about this?
You can add a little bit of random noise.
Yes, exactly. You can add you can do what's called dequantization. The idea is that assume that I was modeling two binary variables, so each of these variables can only take, it could be this one takes here, the first variable takes the value 0 or 1, and the second variable takes the value 0 here or 1 here. Then I can add a little noise to these. In fact, I can sort of add enough uniform noise so they actually become a density like this. And this strategy is called dequantization, and that's also what they apply in real NVP. So they dequantize the pixels, so they actually become a density rather than a discrete distribution. And if you apply these fairly simple transformations and enough of them, then this is what modeling with flows looks like. So, for instance, if we when they apply real NVP to ImageNet, a downscale version of ImageNet, this is the training data. This is what samples looks like. This is Celeb A training data samples. This is the bedroom part of the Elsun data set. To see that you get a generative model that can generate something that looks plausible. It's not working great, but you can see it's still a fairly powerful model with these very simple transformations. There's an extension of real NVP, probably the most famous flow-based model. That's the GLOW model. They apply a bunch of extra tricks. It's still a fairly simple model building on the affine coupling layers. And this is what samples looks like from the GLOW model on the Celeb A data set. But we don't really have details to go into details about how GLOW works. Yes?
Are the parameters of the SMT transformations shared across the layers? The parameters of the SMT transformations.
If they're shared between the layers. No, they're not shared between the layers. You have different parameters for each of these transformations. Yes, yeah, you could also share them between layers. But all these, what happens is that you end up with very large models, because that's an issue with these models. Because you're basically only applying a affine transformation each layer to part of the variables, you end up with super deep models, and you end up with models with a lot of parameters, which is one of the challenges to get something that looks like this. All right, so that was a brief introduction to flows. I just focused on this affine coupling layers. There's a lot of different other layers that you can apply in flows, but the affine coupling layers is probably the one that's sort of easiest to understand, and where you also can understand how you can do this Jacobian transformation. But look in the literature if you want to learn about all the other transformations. I just here towards the end, I just want to mention what can we use flows for. We use them for density estimation, and one thing where they really excel is that you actually have access to the exact likelihood. So many of the deep generative models, particularly VAEs, we don't have access to the exact likelihood. But these are models where if I learn the model and you come with the data point, I can calculate the exact likelihood or density for the data point. And in principle, it can approximate any distribution. We saw sort of a hand-wavy argument for that in the beginning. But the layers are simple, so they end up being very deep. And particularly this GLOW model is like, I can't remember the number of layers. Did I put it on the slide? But it has hundreds of layers as far as I remember. We can also use them for variational inference. So if you want a more flexible approximate posterior, then we can use flow as the variational posterior. We can actually use it in a VAE, but we can also use it for any of the Bayesian models you looked at so far. And we can also use them as flexible priors for VAEs. I'm going to show you an example on the next slide. And use them for many more. There's a whole section in this paper I mentioned in the beginning that's describing how we can use flows. This is just, without showing any of the math, this is just an example where we use the real NVP prior for this simple MNIST-like data set. So this was the standard Gaussian prior you already seen on the previous slide. This is what it look like with the mock prior. And if I use a real NVP prior, then this is the prior in the background, greenish, and then I got the approximate posterior. So we see here, with a real NVP prior, I get a very nice fit between the approximate posterior and the prior of the model. So that was what I wanted to cover. I'm only 10 minutes behind my schedule. So takeaways here is that flows are models for density estimation. They have exact likelihood. They can approximate any distribution. but the layers are simple, so require many, and we use them for flexible posteriors and variational inference, flexible priors and VAEs and more. And if you, like, in a VAE, well, I don't know why I have this note here. I just want to say that, I'll skip this. I just want to do it quick because now I covered flows and I covered VAEs, so I just want to do a quick side-to-side comparison between the models. So in flows, we got exact likelihood, whereas in VAEs, we only got approximate likelihood, so we usually use the elbow as a proxy for the likelihood. Flows, one of the downsides to flows is we have got no dimensionality reduction, so they're not super useful if we want to do semi-supervised learning, whereas VAEs, they got built-in dimensionality reduction. One of the issues with flows is that they don't directly model discrete data. We need to sort of do this dequantization of data. And in fact, they don't work very well for discrete data of discrete nature. For instance, if I have a data set, like a checkerboard data set, so I could have a density that looked like this. This is in fact continuous data so this is samples from my data set. So I got 0 densities in these regions and I got high density in these regions. So the data points are 2-dimensional. So samples would lie in the checkerboard part of sort of on these squares. If I try to fit a flow to this, and if we've got time in the exercise, you will actually try to fit a flow to this. You see that it's very hard to fit a flow to data that looks like this. A VAE can, in principle, model discrete data or things with sort of discrete nature because we have the Bernoulli output distribution on the VAE. But if you try to fit a VAE to something that looks like this, it's also difficult. And then we have this final thing that, if we look, we already talked about this in the beginning, that flows, they perform a bijection transformation of the prior or the base distribution, whereas the VAE, it performs the stochastic transformation because we have this output density. So that sort of concludes what I wanted to cover in this introduction to deep generative models. I just want to mention at the end that if you want to dive more into deep generative models, then we're also running another summer school. Sorry for doing some advertising here, Thomas, but it's actually running next week, so in Eindhoven, so it's too late to sign up. But next year we plan to run it again, and that's a full week where we only talk about deep generative models. And also I'm also looking for a postdoc, if anybody are looking for postdocs in deep generative models. Okay, so that concludes what I wanted to talk about. Then I got another small exercise. It's the same link. There's another Jupyter notebook in there. And the idea is that you're going to implement this mask coupling layer. So there's a whole skeleton for a flow in there, and you just need to put in sort of the 2 transformations and the calculations of the Jacobian. It's only about 10 lines of code you have to do, but I know it's difficult to do in 15 minutes. You were supposed to have a half an hour, and that's even difficult to do. But the TAs will be around, and I'll also be around for lunch. So come and ask me questions if you got questions for the exercises. So that's it. Thank you. So any questions before we go to the exercises? Yes?
You mentioned that normalizing flows can be coupled with VAEs as either flexible priors or posteriors. Are you aware of use cases where normalizing flows are used as flexible likelihoods using protocol for the VAE?
Yeah. So I'll just repeat the question. The question is that we can use flows as we can use them as either a variational posterior approximation, or we can use them as priors. And the question was, you could in principle also use them as the output distribution. And if I'm aware of any work where they use a flow as the output distribution, that's a good question. I'm not immediately aware of any work that does that. I think that the complicated thing about doing that is that in that setup, you would sample a set, and then you would decode it. And what you get out would then be the parameters of the networks of the flow, right? Or something like that. That was sort of that's sort of the network. That's sort of the setup I would have in mind. In that case, the output of your decoder would have to be very high dimensional, right? Otherwise, your output density wouldn't be very complicated. And it was sort of, I could just see it's quite challenging if you wanted to do that setup, because these flows to model something just slightly complicated just have a lot of parameters. Any other questions? Okay, then let's jump to the exercise. I'll just jump to the exercise slide. Cool.